Be a long series for Introduction to Algorithms. Now, I know a lot of college students tend to take this class as a CS major or EE major. It's very helpful, and I would encourage to take this class. For those who think a bit more intuitive and don't quite like the explanations of their professors, which may be vague or too quick to grasp, I think this would be a nice channel to look at. So this is lecture 1. I'll be quickly explaining the general idea of what an algorithm is, because I feel like not many people may understand what it is and may think that it's just too high level of a concept, which it is not. And towards the end, I will, or probably the bulk of this lecture will be on finding the peaks in a 1D and 2D array. So, what is an algorithm? As you can see, algorithms are procedural steps that are given to a computer so that it can take in some sequence or some input or input values and produce a specific and deterministic output value. Which means if I get a list of, say, integers that are not sorted and I wanted a sorting algorithm, then when I give my list as an input, the output should be a sorted array. If you go into like computation structures or any sort of like software development class, they would explain, having correct or accurate specifications that deal with, mutability and things like that. But in terms of just this class, this is specifically about the procedural steps that one may take to achieve an outcome. And secondly, what makes an algorithm good is the efficiency, the runtime that it takes to produce that output. Because most problems have many solutions, but there are only some good solutions, things that solve problems efficiently, accurately, and within a certain amount of time. For example, you don't want to have maybe a really, really slow algorithm dealing with billions of inputs, right? That would nearly break the computer. It's too many inputs to handle, and it can really be a high cost for a company. So let's jump into this. Dealing with 1D peaks. So what does that mean? Say we have a question, maybe you're on an interview, and they ask you to find a peak, not anything specific, not all of them, but just a peak given an array of integers or doubles of some sort of value, right? Some sort of comparable value. So first we need to define some terms. An array. Hopefully you already know what an array is, but just to give a quick definition, it's an assortment or arrangement of elements. Those elements could be of any type, depending on what language you're using, maybe Scala or Python. You can have many different types within an array. Usually if you're using Java or some other sort of very strictly static object-oriented programming language, then it has to be of the same type. But there are ways to get around that. A peak. So a peak would be an element, say we call the array A. So the A of K element, where that element is greater than the element to its right and to its left. So in this diagram I showed, or an array, A can only be a peak if and only if it's greater than C, greater than or equal to C, and greater than or equal to B. So let's prove that, for one, every array does have a peak, because you can't go anywhere unless we know that for sure our algorithm will produce an output. So say you're given an array, A, B, C, D, E, F, G, H, I, J, and someone asks you, is there a peak? So the first thing we need to think of is, what if there was no peak? What if A is not a peak, right? Then for A not to be a peak, it must be less than B. And if B isn't a peak, then B must be less than C, and so on and so forth. But if J is greater than I, then it's considered a special type of peak, which is a cliff. A cliff is, although there's no right element, this element in itself is a peak because it is at the end and it is greater than I. And so right there, that's a very simple, intuitive proof to understanding why in any array there is a peak. Because if you switch any of those inequality signs, maybe G, for example, you take G. If G is greater than F, if you switch the inequality between G and H, say G is greater than H, then right there G becomes a peak. And that could be, without loss of generality, every element in an array. So let's think of a solution. Hopefully you've heard of divide and conquer. It's a very useful and renowned method in algorithms or for solving difficult algorithmic problems. The quickly intuitive approach to solving this problem, this question of finding a peak, would be to go and compare every element in the list. So that would mean, pick out A and say, oh, is A greater than or less than B? If it's less than B, then move on to pick out B. If B is greater than, well, you know that B is greater than A already because of the last comparison. So you only need to compare B to C. If it's greater than C, then hooray, we have a solution. If it's not, then we have to move to the next element. And so if every number of elements in the array, this seems pretty efficient. Like you only have to go through the array one time. There's no extra, for loops or anything of the sort. It's just one for loop down, and that's it. But is this the most efficient way you can do it? Right? Think of a better approach. Think of the way you look in an encyclopedia or a dictionary. When you look in a dictionary and you say, I want to find apple, you don't look through every single word starting from A, right? You're trying sort of divide it perfectly, maybe in the middle of all of the A's, and then say, okay, so is A more, should I go to the right? Should I flip the pages forward, or should I flip them backwards? And that's the type of approach we'll use in this example. So in this case, in order to divide, we'll simply take the middle element, where the middle element would be n over 2, where n is, as I said again, the number of elements in the array. Once you subdivide it, you have the n divided by 2 element. Now, from there, the same way you would do in a dictionary, you're going to compare it to its right and left neighbor. If it's greater than its right neighbor, then you don't want to go to that side, right? Because you already know it's greater than that side. That means that it's good. That's a check. If it's less than its left neighbor or right neighbor, vice versa, it could be either way. You want to go to the side where the middle element is not greater than, because you know that side will, one, have a peak element because it is an array, it's just a subarray, and two, there will be a larger number or some sort of peak in that array that you know for sure is greater than the half element. So I said, there's an array, there's a subarray that does have a peak element. Why is that true though? So that's true because we're deciding to go to the side where the middle element is less than. So if the next element is greater than, so say you have, the half element, the one directly to the right of it, if that's greater than, then we should go to the right side of the array, correct? But why? Why does that produce an outcome? Because even if the next element is less than n over 2, then we know that this dash, the right element to n over 2, is a peak by definition. And we also know that there are no boundary issues because this element directly greater than n over 2 is greater. Directly to the right of n over 2 is greater. And so that solidifies our argument. Now, if the half element is greater than both of them, then hooray, quick and easy, we can return that value. Now let's think about the runtime of this algorithm. So let's call this runtime t of n, where n is the number of elements. So first we have to pick a number from the array, which would be constant time. It's easy to just say, pop out an element. And then we need to compare, and then now think about the sub array, where the sub array is half the size of the original array. So what does that mean? That means now we're in a recursive problem or recursive equation. So now, if anyone's ever taken, discrete math or anything of the sort, it's probably very familiar to you. But just to break it down, now you have a constant, order 1 constant, plus the time it takes to find out the n divided by 2 size peak. In an array. And so on and so forth. So now it's order 1 plus t over n divided by 2. That could be equal to order 1 plus order 1 plus t of n divided by 4. And so now you think to yourself, how many times can I subdivide the array n? That's easy. Log base 2 of n. So now we come down to the equation of the runtime of this equation. Instead of it being order n, now it's just order log n, which is much more efficient than the outcome we had before. Pretty smooth, isn't it? Now let's think about a 2D array, more similar to a matrix. Now say you wanted to find a peak, a peak being, if A was to be a peak, it had to be greater than or equal to B, C, D, and E. Every surrounding corner, it must be greater than or equal to it, right? So now that we have that definition, let's think about how we would solve this. Looks pretty simple. Intuitively, we should be able to find the peak in one column and then find that corresponding peak in that row, correct? That's it, we're done, right? Not quite. The problem with that is, say A is a peak, then we decide to go to the peak or try to find the peak in that row. And then, ta-da, we find F to be that peak. So now F is definitely greater than A, correct? But does that mean that F is a peak of the overall matrix? No, not quite, because G could be greater than F, because G was never compared to A, was it? So how could we solve this problem? There's a different approach, a bit tweaked, but we still are reusing our idea of divide and conquer, which is good. It's good to reuse early ideas. You don't want to always recreate the wheel. So let's think about this. Instead of doing, every single element in the array, which would be n times n, or if it's a n by n matrix, then n squared, which is pretty inefficient, we can cut this down. Let's pick the half point or the half array of the columns. Find that array, and then find the global maximum, where global maximum means the largest number in that array. Right? Now if we find the largest number in that array, and then compare that number to its left and right element, because we already know it's greater than its top and bottom element by definition of the global maximum of that array. Now we compare it to the left and right element and decide whether to go to the right or left. Now the same way we made the decision in our previous 1D case, we do the same exact thing. If it's less than one side, then go to that side. So say for example, we found where A was the global maximum and it's less than C, right? Okay, cool. So let's go to the right side. We could completely wipe out the left side of this problem. We've gotten rid of half of the matrix. Go to the right side, subdivide that. We find that F is the global maximum of that row, correct? And so now we know that F is the largest element on that row and column that they pair up with, correct? So now we will look at the global maximum of that column that F lives in. So now we find that G is that global maximum of that column. and so on and so forth. So then we find that G, for that row, H is the global maximum. And now we can rest assured that H is a peak of the entire matrix. Why? Because if A is greater than B and D, it's less than C and F, and G, and H is greater than G and F, then as you can see down here with the expression that we're left with, H is most definitely greater than all of its corresponding neighbors, B, C, G, and this top element at the top, because we know H is a global maximum for that array or that column. So just to recap, in these two problems we found that divide and conquer is a great way of deducing a solution to a large majority of algorithms. I mean, this is just one of the methods of being able to solve a lot of sorting and, as you can see, peak finding algorithms. That's all for today. Please leave any questions or any feedback you may have. Thank you.